Greetings everyone, I am Marionne Tapado from President Ramon Magsaysay State University, Philippines. On behalf of my co-author, I am pleased to present our paper entitled Modified Densenet-201 Architecture, a Deep Learning-Driven Rice Blast Detection. For the introduction, rice blast disease caused by the Fungus magnaforte oryzae is a severe threat to rice crops worldwide. This disease spreads quickly in warm, humid conditions, especially during heavy rainfall. Rice cultivation faces numerous challenges, with diseases being a significant threat to its productivity and sustainability. So this decrease in productivity would directly impact the income of farmers and lower the overall rice supply in the country. So farmers might face financial challenges as they may have to spend more on pesticides and treatments to manage the diseases, increasing their costs and reducing their profit margins. Traditional methods to manage rice blasts in agriculture is challenging. These methods rely on visually inspecting plants, which can be subjective and prone to mistakes. So this method can lead to wrong diagnosis and delays in treatment. Also, these need trained experts to check the crops, making them laborious, time-consuming, and expensive. The recent study by Saputra, Hindarto, and Santoso during 2023 on classifying rice leaf diseases using the Densenet-201 model achieved an accuracy of only 88.33%. This accuracy level is not high enough for reliable disease detection in real-world application. So to address this issue, the researcher decided to modify the Densenet-201 model, and the goal is to improve its performance and increase accuracy for better disease classification. For the research elaboration, the researcher was used experimental research design. When it comes to dataset splitting, the total number of datasets has 2,000 images, and then when it comes to training dataset, the 70% of 2,000 images was used in training, and the 20% of 2,000 images was used in validation, and the 10% was used in testing. And for the evaluation metrics, the researcher has the accuracy. The accuracy measures how well a model identifies objects or patterns within images. It's calculated as the ratio of correctly predicted images to the total number of images. When it comes to precision, precision measures the accuracy of positive prediction. So it tells you how many of the predicted positives are actually correct. And when it comes to recall measures how well the model identifies all actual positive cases. It shows the proportion of true positives correctly identified by the model, or how many of the actual positives were correctly identified. And the F1 score is a balanced measure of precision and recall. And then the confusion matrix, it breaks down the model's performance into categories like true positives and false positives, showing how well it distinguishes healthy leaves from diseased ones. Next, for the modified Densenet-201 architecture, in this figure, the modified Densenet-201 model addresses overfitting typically seen in fully connected layers of CNN. So to address this, the researcher replaced the top layer with a dense layer containing 1,000 nodes. So FC layers with dropouts are reintroduced following global average pooling, but with reduced sizes of 256 and 64 dense. So this change aims to prevent overfitting and refine features extraction and learning for better adaptation to the specific needs of rice image classification. So it enhances the model's ability to learn from the data, potentially boosting metrics like accuracy, precision, and recall depending on the application and data quality. Next, we have the results. So when it comes to results, in this table, it compares the performance of modified Densenet-201 and base Densenet-201 models. The modified models performs better across all metrics including F1 score, precision, recall, and test accuracy. It has a high F1 score of having 99%, showing a strong balance between precision and recall, while the base model has a lower score of 89%. The modified model also has perfect precision at 100%, meaning no false positives compared to 91% for the base model, which indicates some errors. And in recall, the modified model scores 99%, meaning it detects most positive cases, while the base model scores 89%. And lastly, the modified Densenet-201 has a test accuracy of 99.50%, much higher than the base model's 88.99%. So overall, the modified model shows significant improvement in performance, making it more reliable and effective for classification tasks. And in this figure illustrates the learning process of the base Densenet-201 architecture. It demonstrates that the validation accuracy surpasses the training accuracy, while the validation loss is consistently lower than the training loss. So the graph indicates that the model performs unstable loss. So fluctuating training and validation losses are a strong indicator of overfitting. Next, we have the so in this figure, it illustrates the learning process of modified Densenet-201 architecture. So it highlights the validation accuracy exceeds the training accuracy, while the validation loss remains consistently lower than the training loss. So the graph shows that the model experiences only minor fluctuations in its loss. Indicates that the performance is relatively stable throughout the training. So this indicates that the model performs better on validation data than on training data during the learning process. Next, we have the confusion matrix. So when it comes to confusion matrix, so in this figure, it highlights the performance gap between the base Densenet-201 and the modified Densenet-201 models. So the base Densenet-201 model faced challenges, especially in differentiating between healthy plants and those affected by rice blast. So in first figure, where 22 instances of rice blast were misclassified as healthy. So in contrast, the modified Densenet-201 model shows marked improvement, correctly classifying almost all instances across all categories. So it achieved perfect classification for healthy plants with no errors and performed nearly flawlessly in identifying rice blasts with only one misclassification. So these results suggest that the modifications made to the Densenet-201 model have significantly improved its accuracy and reliability, resulting in a model that generalizes more effectively across all classes and makes far fewer errors compared to the baseline model. So in conclusion, modified Densenet-201 model represents a significant advancement in image recognitions and classification within precision agriculture. Through the integration of global average pooling and the restructuring of fully connected layers, trained using 2,000 datasets, this model achieving an impressive accuracy of 99.50%. Its ability is further supported by various metrics that showcase consistent and remarkable performance across rice blasts and healthy rice leaves. So again, I am Marionne Tapado, and that would be my presentation. Thank you.